There has been a significant amount of noise surrounding the recent launch of the Qwen3 series in the open-source community. Many people are talking about a specific variant often referred to as the Qwen3.6-35B A3B, and the excitement is palpable. This model promises a new level of efficiency for local deployment, but to understand why it matters, we need to look past the marketing numbers and into the actual silicon and software stack. The core of this discussion is not just about how many parameters the model holds, but how those parameters are organized and accessed during inference. Here is the thing about modern large language models. For a long time, the industry assumed that bigger was always better. If you wanted better performance, you needed a dense model where every single parameter was active for every single token generated. This approach works well for raw intelligence, but it creates a massive bottleneck for latency. When you are running a model in a production environment, every millisecond counts. The Qwen3 family, and specifically the architecture we are calling A3B, attempts to solve this through a technique known as sparse activation. To understand sparse activation, imagine a massive kitchen with 1,000 chefs. In a dense model, when you order a dish, all 1,000 chefs are standing at their stations, ready to cook, even if you only need one specific ingredient. This consumes a lot of energy and time. In a sparse architecture, only a few specialized chefs are called upon for that specific dish. The A3B architecture represents a strategic shift toward this kind of hybrid reasoning. It utilizes a mixture of expert structure where the model dynamically selects a subset of its parameters to process each input token. This means that for a simple query, the model might only activate a fraction of its total capacity, leading to theoretical speed gains. However, the reality of production inference pipelines is rarely as simple as the theory. When we talk about latency trade-offs, we are talking about the cost of routing. Before the model can compute the next token, it must decide which experts to activate. This decision-making process, known as the router, introduces overhead. If the routing logic is inefficient, you can end up spending more time deciding who cooks the meal than actually cooking it. In the case of the Qwen3.6-35B A3B flagship, the routing is highly optimized, but for the smaller variants like the one we are discussing, the balance between activation sparsity and routing latency becomes a critical engineering challenge. Now consider this. The goal of the A3B architecture is to enable high-performance coding agents that can run locally. The community has expressed a strong demand for this capability. Developers want to run complex reasoning tasks on their own hardware without relying on expensive cloud APIs. The promise is that you can have the reasoning power of a massive model without the massive inference cost. But to get there, the model must maintain a unified framework with dynamic thinking budgets. This means the model can decide how much computational effort to spend on a given thought process. If the task is simple, it uses a small budget. If the task requires deep reasoning, it unlocks more parameters. This brings us to the current state of deployment. Despite the open-source release, early adopters face significant stability challenges. There are reports of corrupted outputs and generation collapse when using specific inference engines like vLLM on hardware like the B200. These artifacts suggest that the rapid release cycle and the complexity of the sparse activation patterns have not yet been fully ironed out. The routing logic can sometimes get confused, leading to the model selecting the wrong experts for a given context. This is particularly problematic for coding tasks where a single hallucinated line of code can break an entire build pipeline. Furthermore, the technical bugs coincide with leadership changes at Alibaba, suggesting potential internal turbulence affecting the stability of the latest open-source iterations. This context is important because it explains why the software stack feels so raw right now. You are not just testing a model, you are testing a system that is still under heavy development. The community sentiment highlights a strong demand for local deployment, but the current version requires careful engineering to mitigate known inference artifacts. Developers need to tune their inference parameters carefully, perhaps adjusting the top P sampling or the temperature to stabilize the output. The knowledge gap regarding the specific versioning, such as the 3.6 designation, adds another layer of complexity. While the technical reports confirm the Qwen3 family includes dense and mixture of experts architectures ranging from 0.6 billion to 235 billion parameters, the specific 35 billion parameter model with the A3B designation appears to be a configuration within this broader family rather than a completely separate release. This means the architectural principles of the flagship 235 billion parameter model apply here, but scaled down. The sparse activation patterns remain the same, but the routing efficiency might differ due to the smaller parameter count. This distinction is vital for anyone planning to deploy this in a production environment. If you are building a coding agent, you need to know that the A3B architecture prioritizes hybrid reasoning. It is designed to switch between fast, direct responses and slower, more deliberative thinking. This dynamic capability is what distinguishes it from standard language models. However, the latency trade-offs mean that during the thinking phase, you will experience higher token generation times. You gain accuracy and reasoning depth, but you lose the instant gratification of a standard chat interface. The licensing is Apache 2.0, which is a significant win for the open-source community. This allows for commercial use without the restrictions that often plague proprietary models. However, the technical debt associated with the inference engines means that the license does not solve the engineering challenges of deployment. You still need robust monitoring to detect when the model starts generating corrupted outputs. You need fallback mechanisms to handle generation collapse. In summary, the launch of this architecture marks a pivotal moment for local AI deployment. It proves that you can run high-performance reasoning models on consumer hardware, but it comes with a cost. The cost is complexity. The A3B sparse activation patterns offer efficiency, but they introduce routing overhead and stability risks that must be managed. The demand for local coding agents is real, and the technology is there, but it requires a level of engineering rigor that goes beyond simply downloading a model file. As the internal stability issues are resolved and the inference engines mature, this architecture could become the standard for efficient, private AI. For now, it is a powerful tool for those willing to navigate the trade-offs. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.